In the vastness of space, beyond the twinkling stars and swirling galaxies, something invisible is tearing the universe apart. You cannot see it. You cannot touch it. And yet, it comprises 70% of everything that exists. Scientists call it dark energy, and after decades of research, they still don't know what it is. But what frightens them most isn't the mystery itself. It's what might happen when they finally understand it. Imagine standing at the edge of a cosmic ocean, watching waves of space itself expanding faster and faster, pushing galaxies away from each other at accelerating speeds. This isn't science fiction. This is happening right now, as you close your eyes and listen to these words. And the force responsible remains one of the most unsettling discoveries in the history of science. The story begins in 1998, when two teams of astronomers made an observation that would shatter our understanding of reality. They were studying distant supernova exploding stars, so bright they outshine entire galaxies. These cosmic beacons serve as markers across the universe, allowing scientists to measure vast distances with remarkable precision. What they found defied every prediction. The universe wasn't just expanding, it was accelerating. For decades, cosmologists had assumed that gravity, the force that pulls everything together, would eventually slow down the expansion of the universe. Perhaps it would even reverse, causing everything to collapse back into a single point in a catastrophic event called the Big Crunch. But the supernova data told a different story. Something was pushing against gravity, overpowering it, driving galaxies apart faster and faster. They needed a name for this mysterious force, so they called it dark energy. Not because it was literally dark, but because it remained completely invisible to all instruments, all measurements, all attempts to understand its nature. It emitted no light, produced no heat, and interacted with nothing except the fabric of space itself. The discovery sent shockwaves through the scientific community. In 2011, the astronomers who made this finding were awarded the Nobel Prize in Physics. Yet even as they accepted their medals, they admitted something unsettling. They had no idea what they had actually discovered. Think about that for a moment. 70% of the universe is made of something we cannot explain. The ground beneath your feet, the air you breathe, the stars you see at night, all of it represents less than 5% of what exists. Another 25% is dark matter, mysterious but at least somewhat understood through its gravitational effects. But dark energy? It operates on principles that seem to violate everything we know about physics. Some scientists propose that dark energy might be a property of space itself, a cosmic pressure that grows stronger as the universe expands. Einstein had once theorized something similar, calling it the cosmological constant. He later called it his greatest blunder, removing it from his equations. Now, it seemed he might have been right all along. But if dark energy is a property of space, then it raises a terrifying question. What happens when space expands forever? What is the ultimate fate of everything we know? One possibility is called the Big Rip. In this scenario, dark energy continues to strengthen, accelerating the expansion of the universe beyond all limits. First, galaxy clusters separate from each other, disappearing beyond each other's observable horizons. Then individual galaxies dissolve as stars drift apart. Eventually, even solar systems break apart, planets torn from their orbits. In the final moments, atoms themselves would be ripped apart, every particle in existence separated from every other particle, leaving nothing but isolated fragments in an infinite void. Another possibility is the Big Freeze, where the universe expands forever, but at a steady rate. Stars exhaust their fuel and die. No new stars form. Eventually, even black holes evaporate through a process called Hawking radiation. The universe becomes a cold, dark, empty expanse, with nothing but scattered particles separated by impossible distances, existing in a state of maximum entropy cosmic death. Both scenarios play out over trillions upon trillions of years, timescales so vast that human civilization would be nothing but a forgotten whisper in the archaeological record of the cosmos. But they represent something profound, the ultimate end of everything, driven by a force we don't understand. Yet some scientists fear something else entirely. They fear that dark energy might not be constant. It might be changing, evolving, growing stronger or weaker in ways we haven't detected yet. If it's growing stronger, the Big Rip could arrive much sooner than expected. If it's growing weaker, gravity might eventually win, leading to the Big Crunch after all. The unsettling truth is that we're flying blind through a universe that operates on rules we're only beginning to glimpse. Every measurement, every telescope, every satellite launched into orbit provides new data. But the fundamental mystery remains. What is dark energy? Where does it come from? Why does it exist? Some researchers have proposed alternative explanations. Perhaps Einstein's theory of general relativity breaks down at cosmic scales, and what we call dark energy is actually evidence that our equations need correction. Perhaps we live in a multiverse, where our universe is just one bubble in an infinite foam of realities, and dark energy is the pressure from neighboring universes pushing against ours. Perhaps time itself doesn't work the way we think it does, and the acceleration we observe is an illusion created by our limited perspective. Each theory opens new doors, but behind each door are more questions, more mysteries, more reasons to feel simultaneously awed and unsettled by the universe we inhabit. In underground laboratories around the world, scientists conduct experiments trying to detect dark energy directly. They use the most sensitive instruments ever built, searching for even the faintest interaction between dark energy and ordinary matter. So far, they've found nothing. Dark energy passes through everything as if it doesn't exist, yet its effects reshape the entire cosmos. The Dark Energy Survey, a massive project involving hundreds of scientists, has mapped hundreds of millions of galaxies, searching for patterns that might reveal dark energy's secrets. The data grows more precise each year, yet the core mystery deepens. We can measure its effects with incredible accuracy, but we're no closer to understanding its nature than we were in 1998. And this is what truly frightens scientists, not just the unknown itself, but the possibility that dark energy might be fundamentally unknowable. What if the human mind evolved to understand survival on an African savanna, simply cannot comprehend the true nature of cosmic forces. What if dark energy operates on principles so alien to our experience that no amount of mathematics or observation can ever make it truly understandable? As you drift towards sleep tonight, consider this. The universe is accelerating away from itself, driven by an invisible force that permeates every cubic centimeter of space, including the room where you lie right now. It's been doing this since before Earth formed, before the sun ignited, perhaps since the beginning of time itself. And we still don't know why. The equations don't lie, but they refuse to make sense. When physicists calculate what the energy of empty space should be, they arrive at a number so astronomically wrong that it represents the worst prediction in the history of science. According to quantum mechanics, the vacuum of space should be seething with energy particles constantly appearing and disappearing, creating a background pressure throughout the universe. When scientists calculated how much energy this should produce, they found it should be 10 to the power of 120 times larger than what we actually observe. This discrepancy isn't just wrong, it's catastrophically, impossibly wrong. Imagine predicting someone's height would be 1 meter, but they turn out to be smaller than a single atom. That's essentially what happened when theory met observation. Yet the universe exists anyway, somehow avoiding the catastrophic consequences that such enormous vacuum energy would produce. This is called the cosmological constant problem, and it represents one of the deepest mysteries in theoretical physics. Why is dark energy so precisely impossibly weak? It's strong enough to accelerate the expansion of the universe, but weak enough that gravity can still form galaxies, stars, and planets. If it were even slightly stronger, no structures could have formed at all. If it were weaker, we might not be able to detect it. The precision required for this balance is staggering. It's as if the universe is fine-tuned to an impossible degree, calibrated to allow complexity and life to exist. Some scientists find this deeply unsettling because it suggests either extraordinary coincidence or something they're reluctant to name purpose. In the early 2000s, as data on dark energy accumulated, a pattern emerged that made some researchers profoundly uncomfortable. The density of dark energy appeared to be eerily similar to the density of matter in the universe today. This coincidence seemed too perfect to be random. Why would these two completely different things matter, created in the Big Bang and dark energy, inherent to space itself, have comparable densities precisely in our epoch of cosmic history? Some called it the coincidence problem. Others saw it as evidence that we fundamentally misunderstand something about the nature of reality. Perhaps dark energy and matter are connected in ways we haven't discovered. Perhaps we're living in a special moment in cosmic history, which raises uncomfortable questions about why we happen to exist precisely when this balance occurs. The implications spiral outward into philosophical territory that makes even hardened physicists uneasy. If the universe's fundamental constants are fine-tuned for our existence, does that suggest some form of cosmic selection process? Are there countless other universes with different properties, most of them sterile and dead, while we inhabit one of the rare examples capable of supporting complexity? This is the anthropic principle, and it divides scientists deeply. Some embrace it as a legitimate framework for understanding cosmic coincidences. Others reject it as giving up on finding real explanations, a philosophical surrender disguised as science. But the numbers don't care about our preferences, and the numbers remain stubbornly, mysteriously perfect. Deep in the mathematics, even stranger possibilities emerge. Some theoretical physicists have proposed that dark energy might not be energy at all, but rather a field of fundamental property of space that can change over time. They call it quintessence, after the ancient Greek fifth element that supposedly comprised the heavens. Unlike the cosmological constant, which never changes, quintessence could evolve as the universe ages. If quintessence is real, then dark energy's strength isn't fixed. It could grow stronger, weaker, or even change direction entirely. Measurements suggest that if dark energy is changing at all, it's doing so incredibly slowly. But slowly isn't the same as never, and that uncertainty haunts cosmologists who try to predict the universe's ultimate fate. Imagine a force that has been stable for 14 billion years, suddenly shifting. Perhaps dark energy begins to weaken, allowing gravity to reassert control. Galaxies that have been drifting apart would halt their retreat and begin falling back together. The expansion would reverse, and everything in existence would begin the long collapse toward a final singularity, all of space, all of time, crushed back into a point smaller than an atom. Or perhaps dark energy strengthens instead. The acceleration increases exponentially. What was once a gentle push becomes a violent tear. First, the distant galaxies vanish beyond our cosmic horizon, their light redshifted into nothingness. Then nearby galaxies disappear. The Milky Way becomes isolated in an expanding bubble of darkness. Stars wink out one by one as they drift beyond observable space. Eventually, in this scenario, the Milky Way itself begins to dissolve. The solar system breaks apart, Earth spiraling away from a sun it can no longer orbit. The planet itself would fracture, oceans evaporating into space, continents torn into fragments. In the final moments before the Big Rip, atoms themselves come apart, electrons ripped from their nuclei, particles separated from the fundamental forces that bind them. This isn't science fiction. This is a legitimate possibility based on our current understanding of dark energy, or rather, our current lack of understanding. The timeline stretches across trillions of years, but the mathematical certainty of the scenario chills researchers who work through the calculations. And yet, there's another possibility that frightens scientists even more than cosmic destruction: the possibility that dark energy might suddenly vanish. Our universe might exist in what physicists call a false vacuum, a temporary stable state that could spontaneously transition to a lower energy state at any moment. If this happens, a bubble of true vacuum would form somewhere in space and expand at the speed of light, consuming everything it touches. The fundamental constants of physics would change instantly within the bubble. Atoms would cease to function. Chemistry would become impossible. Everything we know would be erased and replaced with ... something else. Something governed by different rules. This is called vacuum decay, and it's one of the most unsettling predictions of quantum field theory. The truly terrifying part? we wouldn't see it coming. The bubble of destruction would arrive traveling at light speed, meaning we couldn't receive any warning signals, because those signals also travel at light speed. One moment, the universe exists. The next moment, it doesn't. No transition, no escape, no survivors. The probability of this happening is infinitesimally small, so small that it shouldn't occur within any timescale we can meaningfully discuss. But small isn't the same as zero, and the mere possibility that the universe could blink out of existence without warning represents a category of existential risk that defies all human experience. Some scientists argue that if vacuum decay were possible, it would have already happened during the extreme conditions of the early universe. The fact that we exist at all suggests we're probably safe, but probably isn't certainly, and the mathematics remains ambiguous on this point. In facilities around the world, experiments probe the boundaries of dark energy's properties. The Large Hadron Collider, despite being designed to study particle physics, provides data relevant to cosmological questions. Space telescopes map the expansion history of the universe with increasing precision. Underground detectors search for any interaction between dark energy and ordinary matter, no matter how faint. Each new measurement refines our understanding slightly, narrowing the range of possible explanations. But the core mystery persists, resistant to all attempts at illumination. Dark energy remains as mysterious today as it was when first discovered, perhaps even more so, because now we know enough to understand how little we actually know. And in the quiet moments between experiments, between calculations, between conferences where brilliant minds gather to share their latest findings, scientists sometimes permit themselves to feel the weight of what they're confronting. They're not just studying an abstract property of space. They're investigating the force that will ultimately determine whether existence itself continues or ends, whether the universe sustains complexity forever or dissolves into isolation and decay. The dark energy mystery isn't just about cosmology. It's about the ultimate fate of everything, every star, every planet, every thought that has ever occurred or will ever occur. And we still don't know what it is. In the winter of 1917, while Europe tore itself apart in the Great War, Albert Einstein sat in Berlin working on equations that would reshape humanity's understanding of the cosmos. He was applying his newly developed theory of general relativity to the universe as a whole, and he encountered a problem. According to his equations, the universe couldn't be static. It had to be either expanding or contracting. But everyone knew the universe was eternal and unchanging. The stars had always been there and always would be. So Einstein added a term to his equations, a cosmological constant that would counteract gravity and keep the universe perfectly balanced. It was a fudge factor, an adjustment made not because the mathematics demanded it, but because his intuition about reality insisted upon it. The universe had to be static, so he made it static. Then, in 1929, Edwin Hubble changed everything. Using the massive telescope at Mount Wilson Observatory, Hubble discovered that distant galaxies were moving away from us, and the farther away they were, the faster they receded. The universe wasn't static at all, it was expanding. Einstein later called his cosmological constant his greatest blunder, removing it from his equations in what he considered an embarrassing moment of scientific weakness. But the cosmological constant wouldn't stay dead. 7 decades later, when astronomers discovered that the universe's expansion was accelerating, they needed something to explain it. Einstein's discarded constant, now called dark energy, returned from the grave of failed theories. The man who dismissed it as a mistake had accidentally predicted one of the most important discoveries in the history of cosmology. The irony is profound and unsettling. Einstein's intuition was wrong about a static universe, but somehow right about the mathematics. A cosmological constant exists, though not in the way he imagined. It pushes the universe apart rather than holding it together, and its existence raises questions that Einstein never lived to confront. What if dark energy isn't a constant at all? What if it's dynamic, changing over cosmic time in ways we're only beginning to detect? Modern surveys of distant galaxies suggest that dark energy's strength might have varied throughout the universe's history, though the evidence remains ambiguous and controversial. Projects like the Dark Energy Spectroscopic Instrument, perched atop a mountain in Arizona, collect light from millions of galaxies, building a three-dimensional map of the universe's structure across billions of years. By comparing how galaxy clusters were distributed in the distant past versus today, scientists can track how dark energy's influence has evolved. The preliminary results hint that something strange dark energy might be weakening over time, slowly losing its grip on the cosmos. If true, this changes everything. A weakening dark energy suggests that the universe's accelerated expansion might someday stop, perhaps even reverse. The Big Rip becomes less likely. The Big Freeze becomes negotiable. But new possibilities emerge, scenarios that depend on exactly how and why dark energy varies. Some theoretical models propose that dark energy is caused by a scalar field permeating space, similar to but distinct from the Higgs field that gives particles mass. They call it the quintessence field, and unlike a cosmological constant, it can change strength over time, responding to the density and distribution of matter in the universe. If quintessence exists, then dark energy isn't a fundamental property of space. It's something more like weather, a dynamic phenomenon that shifts and evolves according to conditions we don't yet understand. And like weather, it might be predictable if we learn the right equations. Or it might contain elements of chaos, making the universe's long-term fate fundamentally uncertain. This uncertainty extends into uncomfortable territory when combined with another mystery: dark matter. The invisible substance that comprises 25% of the universe's mass energy remains undetected by any instrument, known only through its gravitational effects on visible matter. Galaxies rotate too fast to be held together by the gravity of their visible stars, and gas something invisible must be providing additional gravitational glue. Countless experiments have searched for dark matter particles, building ever more sensitive detectors deep underground to shield them from cosmic rays and other interference. So far, nothing. Dark matter interacts so weakly with ordinary matter that it passes through entire planets without leaving a trace. We know it's there, because we can see its gravitational influence, but we cannot touch it, cannot capture it, cannot study it directly. Now imagine if dark energy and dark matter are somehow connected, two manifestations of a single underlying phenomenon we haven't yet conceptualized. Some theories propose exactly this, that the dark sector of the universe, comprising 95% of everything that exists, might be a unified system with dark matter and dark energy representing different aspects of the same fundamental field. If this is true, then changes in dark energy might correlate with changes in dark matter, creating feedback loops that could dramatically alter the universe's evolution. Perhaps dark energy feeds on dark matter, growing stronger as dark matter clumps into galaxy clusters. Perhaps dark matter decays into dark energy over cosmic time, slowly transforming the universe from one dominated by gravitational attraction to one dominated by spatial repulsion. These ideas remain highly speculative, existing at the boundary between legitimate physics and informed guessing. But they represent the kind of creative thinking required when confronting a mystery this profound. When 95% of the universe is invisible and incomprehensible, conventional thinking simply isn't sufficient. In quantum mechanics, another unsettling possibility emerges. The vacuum of space isn't truly empty. It's filled with quantum fluctuations, virtual particles constantly appearing and disappearing, borrowing energy from the universe for infinitesimal moments before returning it. This quantum foam should create a background energy density in space, a sort of pressure inherent to the existence of space itself. When physicists calculate what this vacuum energy should be, they get the absurdly wrong answer mentioned earlier, 10 to the power of 120 times larger than observed dark energy. This suggests either our quantum mechanics is fundamentally flawed, our cosmology is fundamentally flawed, or something is canceling out most of the vacuum energy, leaving just the tiny amount we observe as dark energy. But what could possibly accomplish such precise cancellation? And why would it cancel out almost all vacuum energy, but not quite all of it? The coincidence seems impossibly contrived, yet here we are, existing in a universe where somehow this cancellation occurs to exactly the right degree to permit galaxies, stars, and life. Some physicists propose supersymmetry, a theoretical framework where every particle has a partner particle with opposite quantum properties. In supersymmetric theories, the vacuum energy contributions from regular particles and their supersymmetric partners would exactly cancel, leaving zero net vacuum energy. But supersymmetry must be broken somehow, because we don't observe the partner particles, and that breaking could leave behind just the right amount of residual energy to explain dark energy. The problem? Despite decades of searching, no experimental evidence for supersymmetry has been found. The Large Hadron Collider was expected to discover supersymmetric particles if they existed in an accessible energy range, but so far, nothing. Either supersymmetry doesn't exist, or it exists at energy scales beyond our current technology to probe. Other researchers look to string theory, where particles aren't point-like objects, but tiny vibrating strings, and space has more than the 3 dimensions we perceive. In string theory, dark energy could arise from the geometry of the extra dimensions, from how they're curled up and hidden from everyday experience. But string theory makes few testable predictions and exists more as mathematical philosophy than experimental science. Each theory, each model, each attempt to explain dark energy either creates new mysteries or requires assumptions that feel uncomfortably arbitrary. It's as if the universe is structured to resist our understanding, to remain perpetually one step beyond our comprehension. And yet the observations continue. The James Webb Space Telescope, launched to study the early universe, provides data on cosmic expansion at unprecedented distances and times. The Vera Rubin Observatory, once operational, will survey the entire visible sky every few nights, tracking billions of galaxies and mapping the universe's large-scale structure with exquisite precision. These instruments will constrain dark energy's properties more tightly, determining whether it's truly constant or subtly changing. They'll measure the universe's expansion history across cosmic time, testing whether general relativity holds at the largest scales or begins to break down. They'll search for new phenomena, unexpected signals, anomalies that might point toward explanations no one has yet imagined. But even as technology advances, even as data accumulates, the central question remains maddeningly elusive. What is dark energy? Where does it come from? Why does it exist in exactly the amount and configuration required to permit a universe capable of producing observers to wonder about it? The silence of space offers no answers, only more questions that echo across billions of light years. In the depths of the Pacific Ocean, off the coast of Hawaii, telescopes scan the sky for something unprecedented, a rip in space-time itself. These aren't optical telescopes, but gravitational wave detectors, instruments so sensitive they can measure distortions in space smaller than the diameter of a proton. They're listening for signals that might reveal dark energy secrets, searching for evidence that space itself is being torn apart by forces we don't understand. Gravitational waves were predicted by Einstein's general relativity and finally detected in 2015, a century after they were first theorized. These ripples in spacetime are created by violent cosmic events, colliding black holes, merging neutron stars, the catastrophic death throes of massive stars. As gravitational waves pass through space, they stretch and compress it, creating tiny oscillations that advanced detectors can measure. Some scientists believe that dark energy might also create gravitational waves, though of a different kind. If dark energy's strength varies across space or changes over time, it could generate a background hum of gravitational radiation permeating the universe. Detecting this signal would revolutionize our understanding, providing direct evidence of dark energy's physical nature. But the signals are incredibly faint, buried beneath noise from countless other sources. Separating potential dark energy signatures from the cosmic background requires years of data collection and analysis. The detectors improve with each generation, becoming more sensitive, filtering out more noise, reaching deeper into the structure of space-time itself. Meanwhile, theorists explore ideas that sound more like philosophy than physics. What if dark energy is actually a window into other dimensions? Some theories propose that our universe is a three-dimensional membrane floating in a higher dimensional space. Dark energy could be the pressure from neighboring membranes, other universes existing just a fraction of a millimeter away, but in a direction we cannot point to because it exists in a fourth spatial dimension we cannot perceive. This is brain cosmology, derived from string theory, and it offers genuinely bizarre possibilities. Perhaps dark energy varies because our membrane universe is moving through the higher dimensional space, encountering regions of different pressure. Perhaps we're slowly colliding with another brain universe, and dark energy is the friction from that collision. Perhaps dark energy will suddenly strengthen or weaken as we pass through different regions of the bulk space that contains all possible universes. These ideas make testable predictions, at least in principle. If dark energy arises from extra dimensions, there should be subtle patterns in how it's distributed across the sky, tiny variations that correlate with the geometry of the higher dimensional space. Surveys haven't detected such patterns yet, but they're looking, and the precision of measurements improves each year. Other researchers investigate modified gravity theory's proposals that Einstein's general relativity needs correction at cosmic scales. Perhaps gravity doesn't work the way we think it does when applied to the entire observable universe. Perhaps the equations need additional terms, new factors that only become important across billions of light years. One such theory is called MONT, modified Newtonian dynamics, though more sophisticated versions go by names like TeVS and MOG. These theories attempt to explain both dark energy and dark matter by changing how gravity behaves at extreme distances or in weak gravitational fields. If successful, they would eliminate the need for invisible substances and mysterious energies, replacing them with modified physics. But modified gravity theories face significant challenges. They must explain not just the accelerated expansion of the universe, but also the precise patterns seen in the cosmic microwave background radiation, the distribution of galaxy clusters, the behavior of light bending around massive objects, and countless other observations. So far, no modified gravity theory has successfully explained all the data, as well as the standard model with dark energy and dark matter. Still, the effort continues, because if conventional gravity is wrong, then dark energy might not exist at all. What we interpret as mysterious energy accelerating the universe's expansion could actually be our misunderstanding of how space, time, and gravity interact at the largest scales. The implications would be profound, not just for cosmology, but for physics itself. As research progresses, the dark energy mystery intertwines with questions about the nature of time. Some physicists argue that time might not be fundamental, but emergent, arising from more basic properties of the universe. If true, then cosmic acceleration might not be what it appears. Perhaps we're not moving through time in the way we assume, and what we perceive as accelerating expansion is actually a consequence of how time emerges from quantum mechanics. These ideas push into territory where science meets philosophy, where equations become interpretations, and where different frameworks can describe the same observations but imply radically different underlying realities. Is dark energy real, or is it a placeholder for something we haven't conceptualized yet? Is the universe actually accelerating, Or does it merely appear to accelerate from our limited perspective? In computer simulations, scientists model the universe's evolution under different assumptions about dark energy. They create virtual cosmos, adjusting parameters, watching how galaxies form and cluster, comparing the results to observations. These simulations have become incredibly sophisticated, incorporating gravity, dark matter, dark energy, gas dynamics, star formation, and even the effects of supermassive black holes. The simulations reveal something fascinating. Small changes in dark energy's properties create dramatically different universes. Increase dark energy slightly, and galaxies never formed. Space expands too quickly for gravity to pull matter together. Decrease it slightly, and the universe collapses back on itself before stars can evolve and create the heavy elements necessary for planets and life. Our universe exists in a narrow band of possibilities, where dark energy is strong enough to be detected, but weak enough to permit structure formation. This fine-tuning disturbs many scientists because it seems to require explanation. Why this particular value? Why not stronger or weaker? The multiverse hypothesis offers one answer. Perhaps there are countless universes with different dark energy values, and we necessarily find ourselves in one where the value permits our existence. The universes with too much dark energy remain empty and sterile, with no observers to wonder about them. The universes with too little dark energy collapsed long ago, erasing any complexity that might have formed. This anthropic reasoning bothers physicists who prefer explanations based on necessity rather than selection. But the mathematics doesn't care about our preferences, and the fine-tuning remains, demanding interpretation. Some scientists find meaning in the mystery itself. The fact that we've discovered something so fundamental, yet so incomprehensible, suggests that human understanding has limits, that some aspects of reality might remain forever beyond our grasp. Others see it as a challenge, evidence that we're on the verge of a conceptual revolution that will reshape physics as dramatically as quantum mechanics and relativity did a century ago. In laboratories and observatories worldwide, the search continues. New experiments probe the properties of empty space itself, looking for any deviation from perfect nothingness. Satellite missions map the cosmic microwave background with increasing precision, searching for patterns that might reveal dark energy's origin. Ground-based telescopes track supernova, gamma ray bursts, and other cosmic events that serve as markers for measuring cosmic expansion. Each piece of data narrows the possibilities slightly, ruling out certain theories while leaving others viable. The space of unknown shrinks incrementally, yet the core mystery remains intact, resistant to centuries of human inquiry and technological innovation. And in the quiet spaces between discovery, scientists sometimes permit themselves to wonder, what if dark energy is trying to tell us something? What if its mysterious properties are pointing toward a deeper truth about reality, something we're not yet ready to comprehend? What if the universe itself is more strange, more wonderful, more terrifying than we've ever imagined? The equations wait, patient and indifferent, holding secrets that may or may not ever reveal themselves to minds evolved to navigate the African savanna, now reaching toward understanding forces that shape the cosmos itself. On a clear night, far from city lights, you can see the Milky Way stretching across the sky, a river of stars representing just a tiny fraction of the galaxies in the observable universe. Look at that band of light and consider that it's held together by gravity and dark matter, spinning in a cosmos being torn apart by dark energy. Every photon reaching your eye has traveled across space that's expanding, carrying information from a universe that's accelerating toward an uncertain fate. The Andromeda Galaxy, our nearest large neighbor, appears as a faint smudge among the stars. It's approaching us, fighting against cosmic expansion through the gravitational attraction between our galaxies. In about 4 billion years, Andromeda and the Milky Way will collide, merging into a single larger galaxy. But by then, every other galaxy cluster will have receded beyond our cosmic horizon, carried away by dark energy's relentless push. Future astronomers, billions of years from now, will see a very different sky. The merged Milky Way Andromeda Galaxy will be alone in observable space, surrounded by darkness in every direction. The cosmic microwave background radiation will be redshifted into invisibility. All evidence of the Big Bang, of cosmic expansion, of other galaxies erased by distance and time. If civilizations arise in that distant era, their scientists will look at the universe and conclude they're alone. They'll see a static cosmos consisting of a single galaxy surrounded by infinite empty space. They'll have no way to discover dark energy, because its effects will have carried all the evidence beyond their ability to observe. The truth of cosmic history will be lost to them, hidden by the very force that shaped the universe. This raises an unsettling question. What are we missing right now? What evidence has already been carried beyond our cosmic horizon? What truths about the universe have become unobservable because we emerged too late to see them? Dark energy guarantees that future generations will know less about the cosmos than we do. We live in a special time, perhaps the only time when intelligent life can discover the full history and nature of existence. Unless we're wrong about everything. Unless dark energy isn't what we think it is, and the universe holds surprises we can't yet imagine. Some scientists have proposed that dark energy might be conscious, or at least purposeful, in some sense we don't understand. This idea exists far outside mainstream physics, but the fine-tuning of dark energy's value, its seemingly deliberate calibration to permit complexity and life, makes some researchers wonder if there's more to the story than random chance or multiverse selection. What if dark energy is the universe's way of regulating its own evolution? What if space itself has properties analogous to self-organization, adjusting its expansion rate to optimize for some criterion we haven't identified? These ideas blend physics with philosophy, science with speculation, but they emerge from serious engagement with the mystery of why the universe is the way it is. In 2020, a research team analyzing data from the Dark Energy Survey reported something strange hints that dark energy's strength might vary slightly in different directions across the sky. If confirmed, this would violate the cosmological principle, the assumption that the universe is essentially the same in all directions on large scales. It would suggest that space itself has structure and orientation, that the universe has a grain, like wood. The evidence remains preliminary and controversial. Other teams analyzing different data sets haven't found the same patterns. But if it's real, it would revolutionize cosmology, suggesting that dark energy isn't a simple constant, but rather something far more complex, perhaps connected to the universe's largest structures in ways we don't yet understand. Such a discovery would open entirely new avenues of research. If dark energy has directional variations, then it must be influenced by something, perhaps the distribution of galaxy clusters, perhaps effects from beyond the observable universe, perhaps signals from dimensions we can't directly perceive. The implications spiral outward, each more mind-bending than the last. As instruments improve and data accumulates, scientists inch closer to either solving the dark energy mystery or concluding that it's fundamentally unsolvable with current physics. Some possibilities can already be ruled out. Others remain viable, waiting for the next generation of telescopes and experiments to test them. The European Space Agency's Euclid mission, launched to map the geometry of the dark universe, will measure billions of galaxies across cosmic history, tracking how dark energy's influence has evolved. NASA's planned Nancy Grace Romang Space Telescope will conduct similar surveys with different techniques, providing independent verification and new perspectives. On the ground, projects like the Simons Observatory will study the cosmic microwave background radiation with unprecedented precision, searching for signals that could reveal dark energy's properties or perhaps detect alternative explanations for cosmic acceleration. The next generation of gravitational wave detectors will probe spacetime itself, potentially detecting signals that no other instrument can observe. Within the next decade, these missions will either dramatically narrow the range of possible explanations for dark energy or make the mystery even stranger by discovering phenomena no one predicted. Either outcome would represent scientific progress, though one outcome would be considerably more comfortable than the other. But regardless of what we discover, the fundamental question remains: why does the universe accelerate? Why does dark energy exist in precisely the amount required to permit galaxies and stars and planets and life? Why does space itself seem calibrated to produce observers capable of wondering about these questions? Some scientists believe we'll eventually discover a new fundamental principle, a deeper law of physics that makes dark energy's properties inevitable rather than coincidental. Others suspect the multiverse explanation is correct, and we simply happen to inhabit one of the rare universes where the properties permit observation. Still others wonder if the question itself is somehow wrong, if we're asking the wrong thing in the wrong way. The dark energy mystery might be solved tomorrow through an unexpected observation that reframes everything we thought we knew. Or it might remain unsolved for centuries. A cosmic puzzle that defeats generation after generation of humanity's brightest minds. Or it might be unsolvable in principle, a question whose answer lies forever beyond the reach of beings like us, trapped in three-dimensional space, experiencing one moment of time after another. As you close your eyes and drift into the darkness of sleep, consider that the same mysterious force, slowly tearing the universe apart, is present in the space around you right now, in the gaps between atoms, in the fabric of reality itself. Dark energy pervades everything, pushing against gravity, fighting the force that holds you to Earth and Earth to the sun, and the sun to the galaxy. For now, gravity wins on local scales. You remain on the planet. The planet remains in orbit. The solar system remains intact. But on cosmic scales, dark energy dominates, and will continue dominating for as long as the universe exists. The ultimate fate of everything depends on this invisible, incomprehensible force. Scientists continue their work, driven by curiosity and wonder, seeking to understand what may be fundamentally unknowable. They build instruments of astonishing sensitivity, conduct experiments of breathtaking precision, develop theories of mathematical beauty, all in pursuit of truth about the universe we inhabit. And perhaps that's what matters most, not the answer itself, but the search for it. The human drive to understand, to question, to peer into darkness and demand illumination. Dark energy might remain mysterious forever, but the effort to comprehend it represents something profound about consciousness itself, about intelligence, about the strange capacity of matter to arrange itself into patterns that can contemplate the cosmos. Before you drift into sleep, remember mystery is never truly lost, only waiting to be found. The dark energy that shapes the universe remains as enigmatic today as when first discovered, perhaps even more so. But each question we ask, each measurement we make, each theory we develop brings us closer to understanding our place in a cosmos stranger and more wonderful than our ancestors ever imagined. If you enjoyed this journey through the unknown, subscribe for more relaxing ancient mysteries, and let your curiosity guide you deeper into the questions that define existence itself. The universe holds secrets still, and the search for them continues, one discovery at a time, one mystery at a time, one question leading inevitably to the next.